around here. So today I want to talk about something big, something actually humongous. What is this? The cosmos. What does it contain? Everything that you can imagine. Galaxies in the universe, trillions of stars in the universe, billions and billions of planets, some of which have life like our own in the universe. So, but a natural question that you might have is, where did this all come from? Where did the cosmos come from? Every atom that makes up you and me and this tab I'm recording in, and this entire room, and also every pulsar and every quasar, every neutron star, every black hole, where does it all come from? And to answer that question, we have to rewind like a lot. I'm not talking about some scales like the last century or something like that. We have to go back 13.8 billion years ago. Yes, seriously, 13.8 billion. Okay, so we can do that. We are just using our imagination and creativity. So let's just rewind 13.8 billion years and see what happened. Okay, what do you see? Nothing. Why? Because nothing is there yet. Space and time as we know it has not formed. Matter and energy as we know it has not come yet. Now, approximately 13.8 billion years ago, there is an event known as the Big Bang. Yeah, the universe starts with a bang. But this is not just an explosion. Scientists just believe that there was an event under which the universe started, just like that. And it grew to an enormous size, the size it is today. And it's still growing, by the way. So, the Big Bang happened 13.8 billion years ago. Agree. Now, let's pause for a second. Seem long enough? Not really. It's just a second. What all can happen in a second, right? But, say that to the Big Bang. Just within 1 second, the four fundamental forces of nature, which are the gravity, which holds me to the earth right now, electromagnetism, which holds all the atoms in my body and the stab and in that car outside, everything together. Strong force, which makes nuclei possible. The nuclei contain protons, right? The protons try to repel each other, but the strong force holds them like a glue. Actually, strong force have a connection with something known as gluons. Then the weak force. The weak force helps in radioactive decay and stuff like that. So all of these forces, physicists are still trying to unify them into one singular force. But is it possible? Not really. Till now, no. We have unified two of them, electromagnetism and the weak force, but the other two are just not compatible. But in the just a fraction of a trillionth of a second after the Big Bang, the four forces were together. They were one force. What exactly was this force? We don't know, because we can't even possibly imagine our universe at such tiny time scales. Okay, next, first bits of gravity. Gravity goes another way, and the remaining three go another way. The remaining three are called electrostrong force, and the electrostrong force then splits into the electroweak force and the strong force. The electroweak then separates into the electromagnetism and weak, and finally we get the four forces we are familiar with today. But there is also something else that happens. From 10 to the minus 12 to 10 to the minus 6 seconds, that is maybe a trillion to about a millionth of a second after the Big Bang, we get something known as the quark epoch. Now, this is the time when quarks are formed. What are quarks? You know our lovely friends, protons and neutrons, right? Now, it turns out that what I told you last time, that atoms are indivisible, is not actually true. Protons and neutrons are divisible, and they are made up of quarks, 3 quarks, and they are known as hadrons, by the way. So, the quark epoch is when the majority of all the matter in the universe was quarks. But one thing you have to know about the universe at that time, it was way too hot. It had way too much energy, and right now the quarks too contain a lot of that energy. Where did that energy come from? Right from the Big Bang. So the situation was something like this: a very small volume, and there was a lot of energy inside it. So the quarks had too much energy, so they could not just bind together at all. After some time, they started binding together, and this is known as baryogenesis, because they formed something known as baryons. After that, finally came the hadrons. What are the hadrons? The protons and the neutrons, as I told you. And also a lot of other particles which we won't go into very deep today. But the thing is, protons and neutrons were formed at this point. Now, after that comes the lepton epoch. Now, lepton epoch is the time when there are a lot of hadrons and antihadrons, which are just hadrons but with their opposite charge. They collide with each other, they annihilate, but there are a tiny bit more hadrons than the antihadrons. So that is why we see everything around us here today, because otherwise everything would have annihilated with each other. But when most of them annihilated, the leptons, what are the leptons now? The leptons are another type of particles that consists of electrons and our favorite muons, the tau particles, and the neutrinos, everything like that, and much more. So the leptons started to dominate the majority of matter in the universe. After that, just maybe 10 seconds after the Big Bang, the lepton epoch was from 1 second to 10 seconds after the Big Bang. After that, 10 seconds to a large time, the radiation in the universe was more than the matter. Now, this is pretty absurd when you think about it, but it makes sense when you go deep into it. Because the photons were outnumbering the electrons and the protons and everything else by a huge factor. So, this is known as the photon epoch, when radiation outnumbered matter. Now, after this, we move on a little. The first atoms form. When does this happen? 2 minutes after the Big Bang. 2 minutes after the Big Bang to the 20 minutes after the Big Bang. This is a time when protons and neutrons come together to form hydrogen and helium, mainly. Hydrogen and helium are formed, but they are not the atoms as we know it today. There are no electrons. It is just the nuclei. So, then 100,000 years later, 100,000, that's huge. After that, we get the first molecule. Remember, still no electrons, but surprisingly we get the first molecules. Helium hydride. That was the first molecule of our universe. This was confirmed in 2019. After that, now we skip forward a lot. 370,000 years later, finally the photons start to decrease in number. Actually, the matter starts to increase in number. So now you get the matter epoch basically. This period is known as recombination. Now, what does recombination mean? Till now, I told you that the universe was too hot, that everything had too much energy. Same for electrons. The electrons had too much energy that they did not just want to bind and settle down around an atom. They were free. They wanted to roam the universe, which was very small. So, this was the time, 370,000 years after the Big Bang, that the universe finally cooled down enough and the electrons lost most of their energy and they finally got binded to the atoms. Now, when this happened, the photons, which had no room to squiggle by till now could just go around anywhere they wanted. Now, this is the moment where we get the oldest light we can see, the cosmic microwave background, just a few degrees above absolute zero. Even today, it helps us in deciphering the formation of the galaxies, the age of the universe, and all that stuff. Now, one thing you have to know that is that the CMB is way too uniform. Right, the heat of the CMB here and here is just the same. But if the universe is expanding at a very large rate, that is, then how could these 2 points have had enough time to reach equilibrium? What does equilibrium mean? Basically, if I take a hot rod over here and I take a cool rod over here and I bring them together, then the heat will flow from the hotter one to the colder one until they are both the same temperature. So that is what we see in the CMB, equilibrium. So these 2 points are the same temperature. That means that the hotter region should have energy from the hotter region should have dissipated to the places having lower energy, right? But there could have been no time for this. So this does not make sense. That is why we have to talk about something known as inflation. Just a fraction of a second after the Big Bang, once the universe was very tiny, smaller than a proton actually. Then, during this time, the equilibrium was achieved. There was enough time for the energy to go around from hotter places to cooler places. And when the equilibrium was finally achieved, the universe grew like anything. It actually inflated. You know how a balloon inflates? It starts from this small and goes to this big. It's like that, but in this case, the universe expanded maybe a million times more bigger than its current size, than its previous size actually. The size just after the Big Bang. So this inflation happened at more than the speed of light. But relativity forbids this. Or does it? Actually, no. What relativity says is that the speed of light is the cosmic limit for information, not for space itself. Space itself can expand at any rate we want, which is what we see today with dark matter, but that is the topic for another day. So, this is basically how the universe started. Next, I will do a follow-up video on what happened later because we have to skip forward a lot. But for now, that is it. How the universe started, the Big Bang, how it inflated, and how we get matter as we know it. Thank you for watching Scientific Curiosity. Stay tuned for the next video.